All right, let's dive right into this explainer. Today, we're looking at a piece of engineering that is visually striking and honestly just completely unconventional. We're talking about the opposed-piston engine. If you've ever stared at a standard car engine and wondered, is there a totally different way to build this thing? Well, you're going to want to stick around because this is absolutely going to blow your mind. So imagine this. What if an engine had no cylinder head whatsoever? Picture a setup with just one single cylinder, but it packs two separate pistons inside of it. It entirely ditches that traditional cylinder head we're all so used to seeing. Sounds like a weird riddle, right? But believe it or not, more than a century ago, engineers came up with a design that does exactly that. So how on earth does a machine like this actually work without just flying apart? Let's break it down.
An opposed-piston engine is, well, exactly what it sounds like. It's an internal combustion engine where two pistons share the exact same cylinder. Instead of having one piston pushing up against a solid static cylinder head, you have two pistons directly facing each other. They move toward each other and then away from each other in this perfect synchronized dance. Because of that, the actual combustion space, the chamber where the fuel burns, is formed entirely in the empty space between the two piston crowns.
To really wrap our heads around this, let's compare it to something familiar. Think about your standard engine. It has a cylinder head, it's got complex valves up top to let air in and out, and there's a single crankshaft at the bottom converting that up and down motion into rotation. But with the opposed piston architecture, there is zero cylinder head, literally none. Instead of overhead valves, it relies on ports built directly into the cylinder walls themselves. And since we've got pistons firing on both ends of the cylinder, we suddenly need two separate crankshafts to capture all that mechanical power.
Let's quickly run through the basic physical building blocks so we have the anatomy down before we put this thing in motion. Conceptually, it's brilliantly simple. You've got your single cylinder housing those two facing pistons. Naturally, two pistons mean two connecting rods, and those attached to the two separate crankshafts we just talked about. Add in the intake and exhaust ports integrated right into the cylinder walls, plus the fuel injectors right near the center, and that's the whole shebang. It is a beautifully symmetrical piece of machinery.
Now you're probably wondering, why go through all the trouble of designing it this way? Well, ditching the cylinder head actually does something incredibly important. In a normal engine, the cylinder head holds the valves and seals, right? But it also acts as a massive static metal sponge that absorbs a lot of the vital heat generated by combustion. By removing it, you're physically eliminating a huge source of heat transfer loss, and less wasted heat means more of that energy goes directly into pushing the pistons. Ultimately, that translates to much better efficiency.
Section 1, the engine in motion. Understanding the combustion cycle.
All right, that brings us to the rhythmic 5-step combustion cycle. It's basically the exact same sequence of events you'd find in a standard internal combustion engine, just achieved in a totally different way. Changing the physical volume between these two synchronized pistons is what drives the entire machine. We go from air intake to compression to fuel injection to combustion and finally exhaust. Let's walk through exactly how these two facing pistons pull off the cycle together.
It kicks off with steps 1 and 2, air intake and compression. As the pistons pull apart, the empty volume between them obviously increases. This creates a vacuum that allows fresh air, usually forced in by a supercharger or a turbocharger, to rush in through the intake ports on the cylinder wall. Once the cylinder is packed full of fresh air, the pistons reverse direction. They rush back toward each other, squeezing all that trapped air into a super tight space right in the dead center. Because this air is so highly compressed, its pressure and temperature shoot up dramatically.
And that sets the stage for steps 3 and 4. The true power stroke of the engine. With the air sandwiched between the pistons now highly compressed and extremely hot, atomized fuel is sprayed directly into that tiny space. Get this, because of the intense heat of that compressed air, we don't even need a spark plug here. The fuel just instantly ignites the second it makes contact. This massive sudden combustion event creates a huge spike in pressure that violently pushes both piston crowns apart at the same time. Think about that for a second. One single combustion event is acting on two pistons simultaneously, sending a huge wave of mechanical force out to both crankshafts. And finally, we hit step 5, the exhaust phase. As the pistons are violently shoved outward by that blast, they keep traveling until one of them physically uncovers the exhaust ports built into the far end of the cylinder wall. All those highly pressurized, hot, burned gases escape out the back door, making way for a brand new gulp of fresh air to rush in from the intake ports on the opposite side. Then, the whole cycle starts all over again. The precise timing of the pistons sliding past and uncovering these ports is absolutely critical for the engine to run efficiently.
Section 2, the synchronization challenge, coordinating two crankshafts.
So keeping these two separate crankshafts perfectly synced requires a pretty complex gear train. It's honestly like a high-stakes mechanical ballet. If the synchronization between them is off by even a fraction of a millimeter, the entire routine falls apart. The ports would open at the wrong times, compression wouldn't peak exactly when the fuel injects, and combustion would just completely fail. The engine's greatest strength, using two pistons to do the work of a single cylinder, is inherently tied to its single biggest mechanical hurdle. So, at the end of the day, it really comes down to a delicate balancing act of trade-offs. On the plus side, we have a highly compact combustion architecture, no heat-stealing conventional cylinder head, fantastic power-to-weight potential, and inherently lower heat loss. But then you have to weigh that against the distinct disadvantages. We just talked about the crazy complex synchronization required. On top of that, you're dealing with challenging piston ring sealing, difficult thermal management because of where those hot exhaust ports are sitting, and just an overall high level of manufacturing complexity. It is a very tricky puzzle for engineers to solve.
But despite those manufacturing hurdles, this isn't just some wild theory on a drawing board. Opposed-piston engines have real-world applications. Historically, they've been massive workhorses in military vehicles, huge marine engines, and heavy-duty power generators where that power-to-weight ratio really matters. They've even been tested in some wild aviation concepts over the years. But what's really cool is looking at modern research engines. Today's engineers are actively reviving and refining this exact architecture to find new ways to boost fuel efficiency and drastically cut down on global emissions.
You know, there's a quote from MechVerse that I absolutely love. The more you understand how machines work, the less mysterious the world becomes. I think this engine is a perfect example of that. Taking a seemingly impossible machine, like an engine with two facing pistons and absolutely zero cylinder head, and breaking it down into logical, understandable physics, that is exactly what makes studying engineering so incredibly satisfying.
So this leaves us with the ultimate engineering dilemma. Do the efficiency advantages of entirely rethinking familiar, everyday machines actually justify the added mechanical complexity it takes to build them? I'll let you weigh the pros and cons of this fascinating marvel for yourself. Thanks so much for joining me on this explainer, and keep questioning how the world around you actually works.